So sample problem 5.6, we actually did in class at the beginning of lecture as a Plickers question. And it was great to do because it's conceptual and there's an A, B, C, or a D answer. So it's a great question to do using Plickers. But we had to visualize what was happening and then kind of pick an equation that we felt matched it. So it says the piston cylinder below is depicted before and after a gaseous reaction that is carried out at constant pressure. So that's a piece of information that's important. The temperature is 150 K before and 300 K after the reaction. It tells us to assume that the cylinder is insulated. And we discussed in class the reason for this is that no heat is lost or gained. Okay, so no heat is lost or gained. So the heat change is totally a reflection of what's going on with the reaction. So hopefully everybody sees that this is really a changing variable problem. So it's a changing variable problem. When we have changing variable problems, we can say P1 V1 over N1 T1 equals P2 V2 over N2 T2. And again, if you're trying to figure out how I got that, go back and look at sample problem 5.3, where we introduce the concept of a changing variable problem and how we use this equation. All right, so again, this says these are both equal to R because the pressure, volume, quantity, and temperature relationship between any gas will be equal to R. So we can set these two equal to one another. But right now, they tell us that this is a constant pressure. So this simplifies already to this. So we can see that P1 equals P2 from information in the problem. Tells us constant pressure. There's another variable there that we actually can get rid of as well because of information that they don't give us in the words but in the pictures. Does everybody see that V1 is equal to V2? We can see that there's no volume change. So what that means, again, volume we can cross off. I'm going to kind of come down here. What we can see is that N1 T1 equals N2 T2. Again, I know that there's 1 over for each of those, but mathematically we could actually multiply both sides and get the same equality. So algebraically, make sure that everybody can kind of get to this point. But the key concept here is we can see that there is an inverse relationship between quantity and temperature. So let's put in information that we know. N1 equals some variable, some amount. T1 equals 150 K. N2 equals some amount. And then T2 equals 300 K. So conceptually here, what we need to see is that we have doubled the temperature. So if T2 is doubled, hopefully everybody sees that that means that the quantity must be 1/2. In order to maintain this equality, if we've doubled the temperature, the quantity must go down by 1/2. It must be half of what it is. So let's go ahead and look at our equations and see if we can see what's going on here. So A2 plus B2 makes 2AB. We had 2 moles of gas making 2 moles of gas. That's not decreasing the quantity by 1/2. That's maintaining the same quantity. 2 ABs plus B2 makes 2 AB2s. Well, that's taking 3 moles of gas, right? 2 of these plus 1 of those, and making 2 moles of gas. Well, again, that's decreasing, but not by 1/2. A plus B2 makes AB2. 2 moles of gas makes 1 mole of gas. So that's decreasing, and that's decreasing by 1/2. That looks like it's the right answer, but let's just check out D. 2 AB2s makes A2 plus 2 B2s. We've got 2 moles of gas making 3 moles. Well, that actually increased the quantity. Again, this first one, no change in quantity. So C is the right answer because we will be decreasing the quantity of the gas by 1/2. So again, a qualitative look at our changing variable problem. I was so excited because in class, 4 people got this right. But then when we found out why they got it right, nobody got it right for the right reasons. So hopefully watching this video after the fact helps you understand a little bit more about this qualitative use of our changing variable problem.